Sonia Hammache, Satachi Natasakawat, and James Goodwin. I just said your name wrong of all those names. And the title of the talk is Reaction Mechanism and Nature of Sites During N-Butane Isomerization on Sulfated Zirconia, and the talk will be given by Sonia Hammache.
Good afternoon, everybody. My talk today will be about normal butane isomerization on sulfated zirconia, and I will be particularly interested in elucidation of the reaction pathway in the presence of olefins. Isomerization reactions are known to be industrially important due to the environmental regulations on the amount of aromatics allowed in gasoline, and the need to substitute those molecules with more friendly high-octane molecules. Normal butane isomerization is known to be a good model reaction to study in order to understand the mechanisms occurring on sulfated zirconia. Two reaction mechanisms have been proposed for normal butane isomerization on sulfated zirconia, a monomolecular and bimolecular mechanism. The monomolecular involves formation of a protonated cyclopropyl carbocation that opens to form a defavorable, energetically speaking, defavorable primary carbocation that rearranges to form a isobutane carbocation that dissolves from the surface of the catalyst as isobutane. The bimolecular mechanism involves formation of a secondary carbanion that dehydrogenates to form an olefin. Second step, we have oligomerization of the olefin and the secondary carbanion to form a C8 intermediate species on the surface of the catalyst. After isomerization and betazation of the C8 intermediate, we have isobutane and byproducts. The byproducts are mainly propane, pentane, hexane, and ethane. Sachler and co-workers using isotopic tracing showed that the reaction normal butane isomerization follows a bimolecular mechanism. And recently in our lab, Kim et al. Showed that the mechanism is bimolecular either at low or high temperature and during all reaction time. This brings me to our objective, which were This brings us to our objectives, which were to elucidate the reaction pathway by adding butene. We saw that the bimolecular mechanism involves formation of butene. We use this characteristic of this mechanism in order to understand more the mechanism. And we would like also to determine the role and the fate of the butene molecules in the reaction. For this purpose, we use the NEMI sulfated zirconia hydroxide calcined at 600 degrees Celsius, which has a SO4 content of 1.78% and a VT surface area of 92.54 meters square per gram. The catalyst was pre-treated in situ prior to reaction for 4 hours at 315 degrees Celsius under a flow of air. We use two temperatures to study this reaction, 150 and 250 degrees Celsius. We varied the olefin-paraffin ratio from 0 to 0.13. We used isotopic transient kinetic analysis in order to determine the kinetic parameters, which were surface residence time. Thus, we could relate that to the turnover frequency and the concentration of surface intermediate of isobutane. Here we have the variation of formation rate of iso-C4 with time on stream in the absence and in the presence of olefins. We see that upon addition of olefin, you have a decrease in the activity during all reaction time. However, if we focus at the initial point, which is 5 minutes time on stream, we see that the decrease in the activity was proportional to the amount of olefin added. However, after 30 minutes, in the case of the added olefin, the activity flattens down to almost a zero value. We know that olefins are good coke and oligomer precursor, and if we take a look at the carbon content analysis, we see that as the olefin-paraffin ratio increases, the carbon content increases, and we determine the carbon content after 300 minutes time on stream. We also calculated the deactivation rate constant based on Jumesic's work and assuming that the normal butane isomerization follows a pseudo-first order reaction. We see also that as the olefin-paraffin ratio increases, the Kd increases as well. The effect of olefin does not have an impact only on the activity, but it has an impact on the selectivity to isobutane as well. A typical variation of the iso4 selectivity with time on stream will be an increase. However, upon addition of olefin, we saw a decrease in the iso4 selectivity, and the decrease is more proportional more pronounced at high olefin-paraffin ratio. The decrease is due more to formation of other species such as C6 and C7 and some of the other species that we did not index. Till this point, we did not see any positive impact of olefins, though olefins are intermediate in the reaction. Then we thought that maybe the positive impact of the olefins was prior to 5 minutes time on stream. For this reason, we used an autocentric valve and collected 16 samples and followed the reaction prior to 5 minutes on stream. What we see that in the presence and in the absence of olefin, the reaction follows an induction period. However, the induction period is shorter in the case of high olefin-paraffin ratio. And if we take a look to the first point, which is around 0.3 minutes, we see that due to the availability of olefins, the reaction started quickly in the contrary to the other two cases. However, even if the reaction started quickly, it deactivated quickly also. We used the isotopic transient kinetic analysis to determine the effect of olefins on the kinetic parameters. We first see an increase in the concentration of surface intermediate. This would be expected because olefins are intermediate in the reaction. However, at 5 minutes time on stream, we see a dramatic effect of olefins on the surface residence time, which thus on the turnover frequency, meaning that the olefin we added at 250 degrees Celsius, and in this case I am talking about the trace amount, had a dramatic effect on the activity of the site. It may be deactivated the most active site. However, it increased the concentration of surface intermediate. The increase could not compensate the two negative effects of the olefins on the active site. We decided to move from a dominant effect of the deactivation. Then we worked at lower temperature, and we added trace amount of olefin to the reaction stream. And contrary to 250 degrees Celsius, in this case we see an increase in the initial rate upon addition of olefin. However, after 30 minutes, the catalyst deactivated. The increase that we see here cannot be explained by the amount of olefins we added, because we added almost a very small amount, which if I relate it to micromole per gram of catalyst per second, it will be around 0.010 micromole per gram catalyst per second. Then this increase cannot be explained by the amount of olefin added. If we take a look at the deactivation rate constant, we see that the olefin deactivated a lot the catalyst. We also followed the induction period upon addition of olefin. We see the most important point here to see is that the reaction started quickly in the presence of olefins. as opposed to the case where no olefins were added. Olefins at 150 degrees Celsius had exactly the same effect on the selectivity as in the case of 250. We see a decrease in selectivity with time on speed. The isotopic transient kinetic analysis showed that at 150 degrees Celsius and at 250 degrees Celsius, olefins did not have an impact on the turnover frequency. It's almost the same value within experimental error. However, and actually as in the same case at 250 degrees Celsius, we see an increase in the concentration of surface intermediate. Then we have the positive effect of increasing the concentration of surface intermediate and avoiding the negative impact on the active sites. This is why we see an increase in the initial rate. We ask ourselves a question, because till now we really had more a dominant effect of the activation either at 150 or 250 degrees Celsius. We wanted to understand really how olefins participate in the mechanism of the reaction. For this purpose, we not only control the amount of olefins added, but we control the time of exposure of olefins. We added olefins for 2 minutes at the beginning of the reaction, and then we stopped feeding olefins for the rest of the reactions. And if we see how the activity of the formation rate of SO4 in this case, we see a decrease of the initial activity as compared to the case where there was a continuous feed of olefin. However, we still see an increase in the case where there were no olefin added. But the most interesting point to see here is the way that the catalyst deactivated in the case where olefins were added only for 2 minutes. We see that the olefins had a positive impact even after we stopped the feed. I mean, we put 2 minutes of olefins. Okay, we saw an increase in the reaction rate. But then after that, we stopped the olefin, but we still were able to see the positive impact on the activity. And if we see how this is related on the kinetic parameter, of course, one would not expect a change in the turnover frequency. A continuous effect did not have an effect on the turnover frequency. An exposure of 2 minutes would not have an effect either. However, even after we stopped the feed of olefins, the concentration of surface intermediate was still high. It means that, okay, we stopped the olefins, but still we could have the positive impact that we saw at 5 minutes time on stream in case of the continuous feed. The way we explain this, I will use a cartoon to schematically show the way we are understanding this phenomena is this way. We have olefin at the beginning of the reaction that adsorbs on some site. A normal butane molecule comes and reacts with the olefin added as a secondary carbonium to form a C8 intermediate. After isomerization and beta sessions, we have formation of the molecule isobutane and some kind of olefinic site. After we stop the feed of olefins to this point, the normal butane molecule coming from the reactant stream reacts with that olefinic site to form C8 intermediate, regenerate the olefinic site, and giving isobutane molecule. With time, of course, this olefinic site will deactivate, maybe to form coal. If this is true at 150, knowing that at 250 degrees Celsius the reaction is also bimolecular, we should see exactly the same thing at 250 degrees Celsius. Then what we did, we exposed the catalyst. We introduced olefins only for 90 seconds at the beginning of the reaction. Well, in this case, we see interesting results because we see actually in the case where olefins were only fed to the reactant stream for 90 seconds, they activated the catalyst more than in the case where there was a continuous feed. after 30 minutes, it flattens down to a zero value. And if we see the kinetic, the isotopic transient kinetic analysis, we see that 90 seconds of exposure to olefin were enough to deactivate the most active site. We have almost a same value of turnover frequency in the case of 90 seconds feed or a continuous feed. However, the concentration of surface intermediate was still high. The only reason we could not see the same phenomena at 250 as the one we saw at 150 is because the activation somehow overlapped the other effect. To summarize, I say at 250 degrees Celsius, added olefin deactivated the catalyst, and the deactivation started from the beginning of the reaction. The activation of sulfated zirconia upon addition of olefin was most probably due to a co-polymer formation. However, it is also affected by a decrease in the activity of the most active site. Adding olefin for only 90 seconds at the beginning of the reaction appeared to deactivate the most active site, and it had almost the same behavior as in the case of a continuous feed, although more intermediate were present on the surface of the catalyst. At 150 degrees Celsius, the positive effect of olefins was more obvious due to the slower deactivation, and it was manifested in an increase in the initial rate. Adding butane for only 2 minutes increased the catalyst of the activity of the catalyst during all time on stream. It appears that butane is involved in the formation of more active intermediates. To conclude, butane addition simultaneously increases the number of active intermediates. It contributes to a more rapid deactivation and has a long effect on increased activity. Well, that is seen only at lower temperature. At high temperature, we could not see it, even after its field was terminated. To end, I would like to acknowledge National Science Foundation for their financial support, and to thank you for your attention.
Questions? I have. I'm not familiar with this reaction, so you're saying that you introduced this bimolecular step when you put the butene in. What's the mechanism?
It is bimolecular.
It's bimolecular anyway,
Yeah.
and this just gets it started?
I've read in the literature in a recent paper from the Wolf's group suggests that ppm levels of water, very, very low levels of water, affect this catalyst. Did you take great care to remove water from your butane feeds?
Yeah. I guess the water effect on the catalyst is when we add water on the sulfated zirconia, you hydrate the Lewis acid site to form more branched acid site. And if you shift too much, there is a ratio of Lewis branched acid sites that you need to have a optimum activity. If there is too much water, you might have a very low concentration of Lewis acid site. This is why you might have a negative impact on the activity. But in this case, yeah, I removed the water. I guess this is kind of a separate kind of work. This is more to determine which active sites are involved in the formation of hydrogen. But here it's the olefins. Olefins, if you have too much of olefins in your reactant stream, you will have tendencies to form coal, and then you are actually deactivating your catalyst.
I just want to comment on this. On the clarity asked here, there are two reasons for expecting water in your system. One is the feed gas. So you have butane and basically have to remove traces of moisture in butane. And butane would contain, I guess, ppm at least of moisture. The other source of moisture could be that when you activate your catalyst at like 600 degrees or whatever, then you go to your reaction temperature, which is 150 or 250. While doing this, you may get some moisture coming into the reactor. I think this is something that people have not addressed so far.
Yeah, I pre-switch the catalyst prior to reaction at 315 degrees Celsius. But yes, you are right, there is always some amount of moisture there that maybe I cannot eliminate. Or there is a way to eliminate. I could actually go to higher temperature than 315 degrees Celsius to pre-switch the catalyst, but it was found that 350 degrees Celsius is the good temperature to use in order to have an optimum activity.
Now what I'm saying is that there are fittings in your reactor. You have a reactor made of glass or metal, and there is diffusion of water from the reactor material, and it's unavoidable that your sulfated zirconia would, when you pull it down, would attract some water. And
this is a possibility, yeah. This is a possibility.
Did you have any effort to maintain the initial rate for the bimolecular reaction? Your effort to maintain the initial reaction rate for the bimolecular reaction. Your bimolecular.
I'm sorry.
When you have the olefin involved in the reaction, your initial reaction rate was very high.
Yeah.
Did you have any effort to maintain it?
Oh, maintain it that no, the catalyst will deactivate with thermal stream, but I showed that if we put the olefins only for a shorter time, then yes, maybe I will decrease the deactivation rate. But in all the cases, the catalyst will deactivate after a certain time.
Anything else? Okay, well, let's think